This example has a 2-degree of freedom mechanical system that we want to create the state space model for. And specifically, it will have one input acting on M2, a force acting on M2, and our observables, we want to track the displacements in the system, y and z. So first, we want to find the state space model for the system. So starting point, we need the free body diagrams, multiple, for our system. In our system, we have M1, which has a displacement z, vertical only, and M2 that has its own vertical displacement y. M1 and M2 can translate independent of each other, so z and y are independent degrees of freedom. So free body diagrams, I'm going to start with, well, the top one, M1, and work my way vertically down. So on M1, I will have two forces acting on it. I will have the force from the spring, K1, and from the damper, B1. And that's the only forces acting on this. So from the spring, I will have the spring constant K1 times, now again, I'll establish here, sticking with the given coordinate system z positive down, that K1, that spring, will be put into tension anytime y is positive or z is negative. So K1 times quantity y minus z will be the force in that spring. And in a similar way, B1 will be positive when y dot is positive, so when M2 has a positive down velocity, or when M1 has a negative or upward velocity. So B1 times y dot minus z dot. And that will equal the inertia, which will be in the direction of z, M1, z double dot. And that's the complete first free body diagram. So I'm going to jump down to my second free body diagram there, looking at M2. So M2, I'll just draw it a little bit wider here. I am going to have, assuming tension, also the force in spring K1 and the force in spring B1. And the work is already done for me because I'm assuming tension in both pictures, M1 and M2. The force in the spring is also K1 times y minus z, and the tensile force in B1 is B1 times y dot minus z dot. Now in addition, I do have this applied force going down, u of t. And actually I have another force because it's attached to spring K2. So this K2 is attached to the floor at the bottom and y at the top. The floor doesn't move, so K2 is put into tension anytime y is negative. So I can rewrite this as negative K2 times y. So those are the three forces, well, one applied force and three element forces acting on M2. So K1, the damper B1, and the spring K2, and the applied force u of t. And that is equal to its inertia. So that's going to be in the direction of y, M2, y double dot. And those are the complete free body diagrams for M1 and M2. So I'm going to use these free body diagrams to write my, in this case, two equations of motion. I'll start with free body diagram 1 to create equation of motion 1, some forces along the z direction. So in the z direction, going with it, I will have the arrow K1 y minus z, also positive, B1 y dot minus z dot, equals, also in the positive z direction, M1 z double dot. With the first equation of motion complete, I got one equation of motion from free body diagram 1. That's all I can get out of it. I'm going to write my second equation of motion from free body diagram 2. So I'll just mark those. That's coming from 2, and that's in the y direction. So here, going in the negative y direction, so it's a negative K1 y minus z. I will have a minus B1 y dot minus z dot. In the y direction, I have the k2 spring. Well, it's pointing downward, but it's a negative k2 times y. And then I also have a positive u of t. I'll just write it as u equals m2 y double dot. And that's the complete free body diagram and then equation of motion for the second picture. So those are the only equations of motions that I can create from what I have. Now, at this point, I want to identify my inputs and my state variables. So the input here, I have u, and that's it. There was, again, only one input in this system. So I will denote that over here, that u is just u, which I will call u1. So it seems a little bit redundant, but in this simple input case, we have just this one input. I will generically refer to as u1. Now, a little bit more thought we have to put into our state variable x. So let's see what we have here. I'll just underline all of them so we can see what's happening. Y and z, and y double dot. Okay, I underlined a y dot, a y double dot, a z dot, and a z double dot. So again, it's only really two independent variables, the y family and the z family. So I need to include from each family all but the highest derivative. So what I'm going to do is, based on the order I was given vertically, I'm going to start with z, although the order really does not matter. But I'm going to say I have z and z dot, again, all but the highest derivative. Z double dot was the highest derivative, so z and z dot, and then y and y dot, since y double dot was that highest derivative. Again, I'll emphasize, I could have written this as y dot, z dot. I could have written this as z dot, y dot. All of those are acceptable. As long as I'm consistent with my ordering, that's going to be the important part, because now that I've put it in order, I have decided which is x1, 2, 3, and 4. So that does make a difference at this point. But really all that would happen if you put your state variables in a different order than mine, we're going to get basically the same matrices at the end. However, our rows and our columns are just going to be switched around. But as long as you're consistent with how you've originally named them at this point, that's going to be fine. And so we're clear. I will have my x dot will then be z dot, z double dot, y dot, and y double dot. And that will then be x1 dot, x2 dot, x3 dot, and x4 dot. Now that my input variable has been identified and my state variables have been identified, I am going to go and rewrite my equations of motion in terms of the state variables. So equation 1 I'm going to rewrite now as 1a and replace with state variables all of the original named variables. So I have k1 times y minus z. If I look here, y, the only thing that can be referred to as y is x3. Right? I have no other choices. Minus z, which only appears as x1. So no choice to be made there. Plus b1 times y dot. So here, y dot is x4, but y dot is also x3 dot. I have a choice between x3 dot and x4. I must choose the one that is not a derivative. So I'm obligated to use x4 here. Minus z dot. Again here, I can call z dot x2, but also z dot is x1 dot. I have the choice between x2 and x1 dot. I must choose x2 because it is not the derivative of a state variable. Again, in the mapping equations, we will put in that x1 and x2 are related because they're both z, or related to z, and x3 and x4 are related because they are both related to y. But back to here, equals m1. Now z double dot only appears as x2 dot. I don't have any choice to make. That's the only thing I can write it as. Now looking at 1a, it has only one derivative term, and that's ideally what we want to see. It might be unavoidable that we have more than one derivative term, but this looks good. So before I isolate, I am going to expand my algebraic terms a little bit to make the next step a little bit easier, I think. b1x2 equals m1x2 dot. Now, I want to isolate my one derivative term, x2 dot. So everything is going to have to be divided through by m1. So let's see, I'm going to put it now in the correct order, or ascending numerical order of x's. So I'll have a negative k1 over m1 x1. Now my x2 term, I only have one, a minus b1 over m1 x2. My x3 term, I'll have a plus k1 over m1 x3. And my x4 term, I have a b1 over m1 x4. And that is everything there. So my 1c now has x2 dot isolated, and it's in terms of just my state variables. So 1c I'm going to put aside for now, and I'm going to do the same thing to 2 to create 2a. All right, so here I have a negative k1. Y I can only call x3 minus z, which is x1. I have a b1 y dot, same thing as I had in 1. Y dot can be x4 or x3 dot. I'm obligated to write it as x4 minus z dot, which I will write as x2, minus k2 times y, which is x3, that's the only choice I have, plus u, which is u1, equals m2. Now y double dot only appears as x4 dot. So no choice to make, it has to be a derivative. That's the only place it even appears. And I'll distribute. So negative k1 x3 plus k1 x1 minus b1 x4 plus b1 x2 minus a k2 x3 plus u1 equals m2 x4 dot. Now, like the previous one, I want to isolate that one first derivative term x4 dot, which means everything will be divided through by that m2 term. But I want to be methodical and put my x1 terms, my x2, my x3, my x4, and then my u1 in that order. So looking here, I have k1 over m2 x1, that's my only x1 term. I have only one x2 term here, so plus b1 over m2 x2. And let me just cross these off as I go. Make sure I've accounted for everything. Because here we see that x3, we have actually two terms. I have a minus, I can write it as k1 plus k2 on top, over m2 x3. So this is accounted for, that is accounted for. Both of them are x3s. I just want one coefficient in front of my x3 term, minus b1 over m2 x4. x4 is now accounted for. And I have a u1 term, plus a 1 over m2 u1. And that's it. That's my 2c. x4 dot I have now isolated, and my right-hand side has no derivative terms. That's what I want. Same thing with 1c. I have my one first derivative on the left. My right-hand side has no derivative terms. x2 dot I have an expression for. x4 dot I have an expression for. I don't have an expression for x1 dot. This is where I go to the mapping. I've used up my two equations of motion, but I still need two more equations because I need 4 equations for my 4 state variables. x1 dot, this is the mapping. x1 dot is z dot, but z dot is also x2. Therefore, x1 dot is also x2. Simple as that. And I have now an x1 dot, an x2 dot, an x4 dot. I need an x3 dot expression, again coming from mapping. Coming up here, x3 dot is y dot. Y dot is also x4. Thus, x3 dot is also x4. So this, just so it's nice in columns here, x3 dot equals x4 is my second mapping equation. I have all four equations I need to now write this in my matrix form. So I can write that x dot equals an A matrix times my x1, 2, 3, and 4, plus B times U1, my input. I know up front the A matrix is going to be 4 by 4 because I have 4 state variables. So this is A, and again, 4 by 4. And this will be B, and I know that that will be 4 by 1. I have 4 state variables, but I only have 1 input variable. So 4 rows, 1 column. All right, so let's fill in what we need. So it's going to turn out that equation 3 will actually go first because that's my x1 term, or my x1 dot term specifically. So 0, 1 in front of x2, 0, and 0 in front of u1. That's pretty straightforward. Now I have my x2 equation, which is 1c. So I'm going to bring that down all the way here, and that will form the second row of this matrix equation. So the coefficient in front of x1, I have a negative k1 over m1. I have a negative b1 over m1 in front of x2. I have a positive k1 over m1 for x3, and a positive b1 over m1 for x4. And there's no u, so that will be 0. So that is the second row of, well, the A matrix and the B matrix coming from 1c. Just transcribing 4 scalar equations into 1 matrix equation. Scrolling back down, I will now need my x3 equation next. That will be my third row. And we go back to something pretty simple. x3 is 0x1, 0x2, 0x3, 1x4. And then there's no u1 term. And finally, my x4 equation will come down. That is 2c. And so I need one more color here. So the fourth row, I'm a little bit cramped. I didn't plan quite far enough in advance here. I will transcribe 2c into my fourth row. So I have a k1 over m2x1, a b1 over m2x2, negative quantity k1 plus k2 over m2, and a negative b1 over m2x4. And now here I have 1 over m2 times u1. Now I'll redraw this a little bit so it fits correctly. So now I have my A and my B matrices. Again, A is 4 by 4, B is 4 by 1. So this step is now done. X dot equals AX plus BU. That's the first part. Now I need to fill in my second part of my state space model, my observables. So my Y vector. I am told here my observables will be Y and Z. So coming down here, again, the order I put it in, whether Y and then Z or Z and then Y doesn't matter. I'm going to write it as Z and then Y though, just because that's a similar order to how I assign my state variables, but order doesn't matter. So Z and then Y go into my state variables. Z is X1, Y is X3. So I'll just put in their corresponding state variable names here. Equals my C vector times my X vector. My C matrix times my X vector. Plus, then I'm going to have my D matrix. So this will be C, this will be D, and this is times U1. C is going to be the number of observables 2 by the number of state variables 4. D will be my number of observables by my number of inputs 1. So C, the first row, has to equal x1. 1, 0, 0, 0. When I do that matrix multiplication, I am left with x1. And then 0 for the D matrix in the first row. For my second observable, x3, well, that should be 0, 0, 1, 0. When I do that multiplication, I am going to get just x3. And then again, 0 for that row of my D matrix. And that's my complete C matrix, D matrix for my observability equation, because I was told in the problem that I was tracking Z and Y, or Y and Z. Order wouldn't really matter. Now, had I written Y and then Z here, I would have had X3 on top, X1 on the bottom. So my rows of C would have been flipped, and technically my rows of D would have been flipped as well, although in this case they're both 0. So again, we want to pay attention to the size of C and D to make sure that the linear algebra is going to work out, that C is 2 by 4, and D, even though it's a zeros matrix, still needs to be sized appropriately so that I am going to get the right linear algebra calculations when I actually do the calculations later. So taking in my entire state space model here, I have x dot equals ax plus bu. I have y equals the cx times du. So how did we get here? Going back up, starting at the diagram for this mechanical system, we had 2 independent degrees of freedom. So I drew 2 free body diagrams, M1 and M2, each got a free body diagram. From each free body diagram, I was able to get an equation of motion, giving me a total of 2 equations of motion. Looking at the 2 equations of motion, I determined my input variables. In this case, there was only one of them, u, and my state variables. Looking at what I had here, my highest derivative terms were a z double dot and a y double dot. Therefore, z dot, all but the highest, were state variables. Y and y dot, all but the highest derivative, were also state variables. The order I wrote these in does not matter as long as I'm consistent in what I'm now starting to call x1, 2, 3, and 4. I took my 2 equations of motion and I rewrote them in terms of my new state variables, eventually getting to 1c and 2c. I now have expressions for x2 dot and x4 dot, but I need an equation for each of the derivatives of my state variables. So the other 2 came from the mapping equations. x1 dot is also x2 because of the relationship between x1 and x2, both being in the z family. Same idea, x3 and 4 are both in the y family, and that led me to my 4th equation that x3 dot was also known as x4. I took equations 3 and 4, 2c and 1c, and put them into my now matrix equation for the state space model. X dot equals ax plus bu, filling in the rows coming from each of my 4 equations that I wrote above. Once that was complete, then I went to my observability equation. I was told in the problem that I was observing or tracking both the displacements z and y, which also are known as x1 and x3 by how I assigned my state variable names. So I had to create the C matrix and the D matrix such that Cx plus du equals my observables, x1 and x3. So the first row has to be 1, 0, 0, 0, so that when I multiply, I am left with just x1, the z displacement, and then a 0 because u1 does not factor into my observation. For the second row, it must equal x3. 0, 0, 1, 0 will do that for the C matrix. And again, a 0 in the D matrix because there's no u1 for my second observable x3. So in total, that is what I get for my state space form, my state space model for this 2 degree of freedom system.